the exam before we actually get started. As you know, the exam is this Wednesday. It's held in lecture hall. It technically starts at 8 a.m. Will you get any rounds and come in and start? There's not really meant to be any time pressure on this exam. I will say this: read the entire paper. Right? Read the exam and then decide as to which parts of it you're comfortable with and start before you know. That way you get into the swing of things, so to speak, and presumably the rest makes sense later. The exam has 3 sections. The first section is concepts, which is a bunch of multiple choice questions, look through your worksheets and exercise for examples. The second section is calculations, which is 4 really short calculations. Those are like typical word problems. And the third section is 1 long problem with a little bit of drawing, a little bit of math, just a bunch of fun stuff. Right, remember the point of the exam. It's not just to test how much you know, it's for you to be able to effectively communicate how much you know, right, or whoever is reading it. Which basically means show your steps. This is not an math test, but we are interested in knowing that you can correctly identify different decision points. Right? Remember, the 2 things right? And honestly, start with the calculation first if that's what you're most comfortable with. Word problems, the equations, kindly get into the feel of things. The concept section typically involves a little bit of reading and a little bit of thinking. Right? So give yourself some time and wake up early. Don't saunter in half asleep with some coffee. Waking up during the exam is generally frowned upon. Okay. Now, the rest. For this week, you will have homework as usual. Again, becoming available today, due next week. It is, on the other hand, a very, very small homework. So focus on the exam till Wednesday. You'll have enough time after that to get to the homeworks. Coverage is everything that was covered till the end of Wednesday last week. So the stuff we do today is not is not on the exam. This one will be on the next one. Okay, our story so far, we've been talking about Newton's laws of motion and applying them to situations of law. The main law we use, at least mathematically, is Newton's second law, which is the sum of all forces, a net force acting on an object, must equal the mass times the acceleration of the object. So, the first part of this semester, right, in the beginning, when you started doing kinematics, you studied motion. So, how an object is moving, which direction is moving in, how its velocity is changing. Newton's laws starts trying to explain why it was given to acceleration. In order to go from acceleration to actually motion, always remember to look at the direction of the acceleration vector with respect to the velocity. Right? How these 2 vectors are oriented with respect to each other determines what that particle is going to do. Okay? So if A and B are in the same direction, it's going to speed up. A and B are in opposite directions, it's going to slow down, and so on. Okay. Now comes the actual part. So technically, this was supposed to be a TA taking a bucket of confetti. It's supposed to be a bucket of water, but water is kind of heavy, so there's confetti inside. And my TA started in front of somewhere. So you guys get to see me swing a bucket over my head. Now, if it falls or I get hurt, and the previous instructors noticed that, do not panic. Everything will probably be okay. You'll still have an exam on Wednesday. Okay, so the idea is that I swing a bucket filled with confetti in a vertical circle, right? And the question is the confetti going to fall out? No, right? Unless I'm planning to make a really big mess about this one of us. The question then becomes, why not? If we look at the forces acting on the water in the bucket, so water, confetti equal for now. If I draw a free body diagram of a vertical upside down bucket, right, filled with water, and I look at the forces acting on the water, I have the weight of the water, right, acting straight down, And I have the normal force acting straight down, right? Because the water is pushing up on the surface of the bucket, so the surface of the bucket is pushing down on the water. Correct? Okay, so those are the only two forces acting on said bucket. Right? What's the direction of the net force on the water? Down. Right? So why doesn't the water come down? Still have to look at how that acceleration, how that net force, which is producing an acceleration, is oriented with respect to the velocity of the object. Right? So the stuff in the object, the stuff in the bucket, the water or the confetti, is going in a circle. Right? So it has a velocity vector, and it's pointing tangent to that circle. Right? So the acceleration of the system points perpendicular to this velocity vector. Right? Those forces are perpendicular to the velocity. Right? So the net force or the acceleration is therefore perpendicular to v. What happens when it is perpendicular to v? How does an object move? The acceleration is perpendicular to the velocity. Those are the symbols. Does that make sense? So the reason it doesn't fall down is because v is actually perpendicular to it. Right? So the force on it is causing acceleration, but it's causing centripetal acceleration. Right? It's making it go in a circle. Does that make sense? Right? So we analyze a few more situations this way. So right at the top, V points tangential to the circle, the weight and normal force point downwards. At some side point in the motion, normal force again is pointing towards the center of the circle, weight is pointing straight down. At the very bottom, that's what the free body diagram will look like. Normal force should point up, weight points down, and on that side it should look that way. Remember, you should, in order for an object to move in a circle, you always need a force pointing towards the center of the circle. Right? Because an object moving in a circle is by definition eccentric. velocity is changing direction continuously. Right? In order for velocity to change, we need A. Right? And A must be perpendicular to B in order to change the direction. If A is below B or anti-parallel to B, we change the magnitude of B. Speed it up, slow it down. Right? It is pushing it or it is stopping. But if A is doing this, it's going to make it go. Right? You can try yourself. Just push perpendicularly down while trying to move your hand. Then do this. Right? If I'm always pushing perpendicular to B, I get an object to move this way. What the force at the top, what that net force at the top is going to narrow is producing is a centrifugal acceleration. Right? There is a net force on that water at the top. Right? But that net force is pointing straight down, like you saw. Right? But V is pointing down. So what this is going to do is that. Right? The force produces a centrifugal acceleration. Right? All acceleration is a result of forces. Okay, if I want a centrifugal acceleration, I need a force pointing towards the center. Does that make sense? Okay, let's do a slightly different example. I'm going to consider a ball whirling in a vertical circle. Right? So that's the ball at the top of its motion, that's the ball at the bottom of its motion. Right? And it's attached to a string, and that's why it's going in a vertical circle. Everyone with me so far? All I've done is attach the ball to a string and twirl it around and around in a vertical circle. Okay? So if we consider the forces acting on this object, let's say at this point, right? What are the forces acting on the object at the base of the motion, like at the bottom of the circle? Anyone? Weight, straight down. So this ball has a weight, mg. What else? Is it sitting on something? Normal force only comes about if it's sitting on something. Right? It's a contact force. Right? So if stuff isn't sitting on something or touching something, there's no normal force. What other force must be there? The ball attached to a string. Tension of the string, right? Acting along the string. So there should be tension, which I'll call T1, pointing up, right? When the ball is at the bottom. Everyone with me so far? Okay, now consider the top of the circle. What are the forces acting on the ball at the top? Still weight and still tension. There's still tension in the string, and then the ball still has weight. The directions of those forces now, mg acts straight down, and tension acts straight down. Okay. From experience, just think about this. Will these two tensions, the tension at the bottom of the circle and the tension at the top of the circle, be equal? It's a ball whirling in a vertical circle with a uniform speed. Right? So the speed of the ball is just the velocity direction. Right? I'm asking you to think from experience right now. Don't worry about the math. The tension in the string as this ball is being twirled in a vertical circle, where is the maximum and where is the minimum, or is it the same everywhere? Another way to think about it is, where is this ball or a string most likely to break, and where is it most likely to go flat? The slack one is easy. Where is the string most likely to go flat? Right at the very top, right? To swing that bucket fast enough. Does that make sense? Otherwise it goes slack and everything comes falling down. Right? So the tension at the very top must be less. Does that make sense? Right? A string that's about to go slack is very little tension. Right? Similarly, a string that's about to snap has a lot of tension. Right? So where is this thing most likely to snap a string? At the very end. Right? And mathematically, you can see that because if you think about this object, right? It's moving at this point and it's moving at this point. Let's consider the forces acting on it right at the very bottom. Okay? So sum of forces must equal mass times acceleration. That is Newton's second law. Right? The two forces acting on this are tension and mg. T1 at the bottom and mg at the bottom. They are in opposite directions, so I'm going to put T1 minus mg equals ma. What is a for an object moving in a circle radius or with constant velocity? With constant speed? V squared over r. Right? It's centripetal acceleration. So it's producing a, which is v squared over r. So this is v squared over r. Right? So this is how we apply Newton's second law for centripetal motion problems. Right? It's sum of forces along the radius must equal mv squared over r. Right? Just like you did, sum of forces along x-axis and y-axis equals ma along the x or the y. Right? It's sum of forces along the radius equals mv squared over r. Right? mv squared over r has a direction pointing towards the center of the circle. Right? Okay. So any force that points along the center of the circle is taken as positive. And any force that points away from the center of the circle is taken as negative. Right? So it's always plus along the radius and negative away from the radius. Does that make sense? Okay. So we can see that the tension at the bottom of the circle T1 comes out to be mv squared over r plus mg. Right? And now consider the top. I have two forces, T2 and mg at the top, and both of them are acting along the radius. Right? Both of them point towards the center of the circle. So at this point, when I write Newton's second law for the top, it's T2 plus mg must equal mv squared over r. Does that make sense? Right? mv squared over r is a net centripetal force pointing towards the center. Right? Every force that points towards the center acts. Right? It's in the same direction. Correct? Okay. So when we solve this for T2, you find T2 equals mv squared over r minus mg. Right? Their math forms aside, look at those two terms. Right? It's telling you that tension at the top is less than tension at the bottom. Right? It's also telling you that if it's not moving fast enough, right, it is likely to go slack. It's also telling you that as V increases at the bottom, as V increases, the tension increases. So the faster the thing is spinning, the more tension there is. The more tension there is, the more likely the spring is to snap. Does that make sense? So it's more likely to snap at the bottom, much more likely to go slack at the top. And let's say for kicks that this thing, which is moving in a circle in this direction, decides to snap right there. What is this particle going to do? Is it going to do this? Is it going to do this? Is it going to do this? Let's call this A, B, C. Which path does it take if the string snaps? A, B, or C? How many people for A? That's very encouraging. How many people for B? Good. Okay. So it is B. It goes straight. In the absence of any force, its velocity here is tangential, right? So it will continue with that velocity. Correct? Right. Okay. So the idea with centripetal motion is you always require a centripetal force, which is a result of other forces. So centripetal force isn't a new force, right? You need some force to provide centripetal force. So over there it was my arm pulling on it, right? In a radial direction, as this thing rotated. Ball on a string, it's tension. Basically some force that points towards the center of that circle. Otherwise, you're not going to get this thing to move in a circle. Right. So centripetal acceleration is given as v squared over r. Substitute that as the end result in Newton's second law. Right? It's sum of forces equals ma. A for centripetal motion equals v squared over r. Okay? And always remember that this force will point towards the center of that circle. Okay, I'm going to open a this is now a horizontal circle at a constant speed. And of these four forces, only one force points towards the center of that circle. So at least that one is required. Right. Okay. Click something if you haven't so far. It's not going to go in a circle. You need at least, like, how much force you need, right, to make it move in a circle depends on mass, speed, and the radius of that circle. It's mv squared over r. More massive objects require more force to turn in a circle, right? The sharper that turn is, the smaller the r, the more force is required to turn in a circle. The faster you're going, right, the higher v is, the more force is required to go in that circle. Okay? Right. So you need A. So the answer was A. Okay, I'm actually not opening this question up yet. We're going to discuss how you turn your car. This is something I enjoy turning the car on. Right. Let's say I want to turn my car at a nice constant speed, which means I'm undergoing uniform circular motion. Which force is responsible for the centrifugal force required to turn your car in a circle at some speed? Is there any tension? No, right? Unless we attach the car to a spring, there's no tension. Which force gives me the required centrifugal? Static friction. Very good. The static friction between the wheels of the car and the ground is what actually gives you the centrifugal force required to turn. It's not kinetic friction. Kinetic friction is what you get when your tires slide over the road. Right? So as I'm guessing you guys drive in New England, this is not something that you haven't experienced, right? You're on a scale, you can do whatever you want with the steering wheel, it really doesn't matter once you start sliding. Correct? Right. So what's actually helping you make a turn is static friction. The point of contact of that tire with the ground has to stay stationary. Right? So when you turn it, it wants to go that way. Right? But it's feeling a force that way. And that force is static friction. It's not allowing it to move outside along the radius. Right? So it's sending the force inwards, perpendicular to its radius. Right? The car only turns when I turn the tire. Does that make sense? Right? And it's not sliding friction. Sliding friction, kinetic friction, can never In order to turn it, you need a force perpendicular to it. Does that make sense? Okay, so let's consider a car of mass m, right, rounding a curve of radius r with a speed v. Everyone with me so far? Let's consider the top-down view. So that's the circle it's rounding. That's the car. And that's the radius of the circle. Right? Okay, this is the top-down view. What force must be present in this view? A centripetal force which is provided by friction. So friction must go in this diagram. And what must be the direction of friction? Remember, this is a top-down view of a car around the curve. Right? If the car is turning in a circle thanks to static friction, what must be the direction of static friction? Towards the center of the circle. Okay. So static friction points inwards. Right. Now let's draw one more free body diagram, and this is the head-on view. So this is the car of mass m coming straight at you, and since you're a good physics student, you decide to draw a free body diagram looking straight at the car. What forces do you put on it? What forces act on the car? Weight, straight down. That's mg. What else? Normal force. It's sitting on the ground, so n. What else? Static friction. In what direction? Towards the center of the circle, which looks something like this. As opposed to kinetic. So kinetic friction is, instead of doing this, right, in order to turn, this point needs to be stationary, right? Otherwise I won't move it. Right? Kinetic friction is this. Right? So there's no way I can. Okay. So those are the forces acting on it, and these aren't balanced. Right? These do not add up to zero. And they shouldn't. This object is undergoing acceleration. It's moving in a circle. Right? So these forces should not add up to zero. Right? In the vertical axis, they add up to zero because the car is moving on the axis. Right? It's not accelerating in the vertical axis. Does that make sense? So as far as the y-axis is concerned, for this problem, sum of forces in the y must equal mass times acceleration in the y, which gives me n minus mg is equal to 0, which tells me that in this case the normal force is equal to mg. Right? It's a nice horizontal surface, so yes, the normal force will come out to be equal to mg. There's no acceleration in the vertical. Okay. The other equation that you're going to use is along the radius. So sum of forces along the radius must equal mass times acceleration along the radius. Right? That's your centripetal force equation. Over here, AR is the centripetal acceleration. V squared over R is not zero as long as the object has some speed and is moving in a circular radius. Does that make sense? Centripetal acceleration does not require the magnitude of V to change. Right? Just the direction. So any V going in a circle still involves centripetal acceleration. So now let's put in the radial forces. I only have static friction along the radius. Right? These two forces, the normal force is pointing this way and weight is pointing into this. Right? They don't act along the radius. Which gives me that the force of static friction must equal mv squared over r. What can I substitute for the force of static friction? What must that be equal to? This Cartesian over. What must static friction be? N mu s, right. So mu, which is the coefficient of static friction, times the normal force must equal mv squared over r, which implies that you can write this as mu s times mg equals mv squared over r. M goes away, which tells me that v squared is mu s rg. So v is under root mu s rg. Okay, forget about the math for a second and look at what that result is actually telling you. Right? First of all, it's telling you the speed with which you can safely round this curve, right? When you have enough centrifugal force to round the curve, depends directly on mu s. Which should make sense. The stickier the surfaces are, the easier it should be to round the curve. Right? The faster you can go rounding the curve on a sticky surface as opposed to a sliding surface. Does that make sense? Okay. The other thing is directly related to, of course, is the radius of the curve. Remember, a large radius curve is a nice gentle curve. Right? So a large radius curve, as you guys, especially getting onto that connector, that really nice radius curve, you can go pretty fast. Right? Not that you should, there's generally cost bar right by the connector. But the idea is, on gentle cars, right, in long cars, you can get more speed because you don't require that much centrifugal force. Now, what does this result not depend on? Right? It is independent of the mass of the car. Right? So, how fast a car can round a curve shouldn't matter whether it's a big drop or a little drop. Does that make sense? But the acceleration is around the same. But that actually takes the same amount of force to make a drop go in a curve as opposed to a smart car going in a curve. Does it take the same amount of frictional force? No, it takes more for the drop to produce the same acceleration. Right, remember F equals ma, right? We're getting the same acceleration in the smart car and the truck. In order to get the same acceleration in the smart car and the truck has to feel like a lot of force because it has more mass. Does that make sense? But ultimately, the speed at which the truck rounds the curve and the car rounds the curve depends purely on the curve itself and the tire radius, not the mass. Does that make sense? Okay. Now you can answer the conceptual question. That's this guy. Okay. I think I just started the new poll. Yep. Okay, click something. I'm not sure if I should be showing you guys this, but as long as it gets the correct answer, I'm fine with it. For the exams, this doesn't work. Right, click something. There should be no difference, right? If the question, on the other hand, asks which requires more force to round a curve, the answer, of course, is the truck. Right. One more quick concept question. So if you look at this diagram, why am I doing the question? It's basically a Formula 1, right? And you see a lot of those, like a lot of the lines, which is basically, thread left on the graph. A lot of the lines follow that nicely curve, correct? But some of them are going straight. Very good. Right, click something. Oops. Okay. Right, that ends chapter 5. So before we start chapter 6, right, the story so far is what it has. So the first part is kinematics, where we use velocity, acceleration, and displacement to describe motion. Right? The second part was dynamics, which is where we start studying how motion is impacted, essentially how we can use acceleration. Right? So the way these two are linked to each other is always the relationship between A and B. Right? So you have a system. The sum of all forces acting on an object is mass times the acceleration of that object. Right? So you can find the acceleration of a system from Newton's laws. Once you have A, in order to figure out what the object will do, look at the direction of A and B. If they're in the same direction, B will speed up. If they're in opposite directions, B will slow down. Right? And if they're perpendicular, it will move in a circle. The magnitude of B will not change. Everyone with me so far? In every situation in the middle, where it's not perfectly perpendicular or perfectly parallel, can be broken up, and you can think of along the perpendicular axis and along the parallel axis. And then the perpendicular stuff will make stuff move in a circle, and the parallel stuff will slow it up and speed it up. Does that make sense? Okay. Now we come to work and energy, which is probably the most important topic for this semester. And it's pretty basic. It's actually very, very straightforward. Easy to mix up though. Right, let's start with work. So now when we say work in general, day-to-day life, we need a whole bunch of stuff, right? Technically, I'm working. When it comes to physics though, the term work has a very, very specific definition. And now we're talking about mechanical work. So in order to talk about work, in physics we can't be that different. We talk about work done by specific forces, or we talk about the network. Where the network is the work done by the networks. Everyone will say so. Right? So in physics, it's not possible for me to say go find a work. Right? I have to be more specific. It has to be go find a network, or go find a work done by a specific force. Everyone with me so far? Right? There's no general thing like work. There's a network and there's work done by specific forces. And the network is the sum of the works done by all the forces on it. That makes sense? Okay. Now, the definition of work, mechanical work, is F d cosine theta. And I'm going to come to what each of those mean. So work is W. F is the force I'm finding the work done by. So this expression gives you the work done by a force F. Okay? D is, well, theta is the angle between F and D, where D is the actual displacement or distance along one dimension. So take a minute to understand that. Cosine theta here, we're not talking about an incline, right? This theta, in this definition, is the angle between two vector forces. Right? I have force, which is a vector, I have displacement, which is a vector. Theta is the angle between those. Okay? So let's consider some straightforward examples. I have an object like this. If I apply a force in this direction and it moves, so its displacement is in that direction as well, right? So that means I have F in that direction and D in that direction. Those are my force and displacement vectors. What is the angle between them? 0. And what is cosine of 0? 1. Right? So when F and D are parallel to each other, right? So they point in the same direction. Work, which is F d cosine of theta, becomes F d cosine of 0, which is just F times D. That makes sense? Right? theta in that definition is the angle between the force vector and the displacement vector. So now consider the same block moving, I'll call that F1. Let's say that there's a force F2, which in this case is the normal force, right? And I want to find the work done by the normal force in moving that block. Right? So that work is Fd cosine theta. In this case, F2 points that way and D points that way. W is F2 times D times cosine of the angle between F2 and D. What is the angle between F2 and D? 90. Right? And what is cosine of 90 degrees? Anyone? What's cosine of 90? 0. So the work done is 0. Now, think about this for a quick second. Right? What we're saying is the normal force in this case, right, which is the perpendicular force there, right, does no work in taking that object to distance d, which should make sense. The normal force is perpendicular to the displacement. It had nothing to do with moving that object. Right? So if the force is perpendicular to displacement, it doesn't work. Everyone with me so far? We have one more case. And let's say there's a force of friction, which I would call F3 for now. And obviously, if this thing is moving that way, friction would act that way. Correct? Which means if I find the work done by friction, it's Fd cosine theta. So I've called friction F3, D is the distance, and now I have to find the angle between a displacement in that direction and a force in that direction. What is that angle? Is that 0? No, it's 180. What is cosine of 180? Anyone? Cosine of 180 degrees minus 1, right? Which gives me that this is minus F3 times D. So it comes out to be negative. Okay, a few things about work. Work is measured in joules. The SI unit of work is joules. Is work a vector or a scale? Very tempting to say that. Work is actually a nice easy scale, just a number. Work has no direction associated with it. Right? Work done by a force is work done by a force. The pluses and minuses, therefore, are not the means. Right? One thing about vectors and scalars, on a vector, a plus and a minus is a direction. Right? Minus A is a vector pointing in the opposite direction in the same manner. Right? On a scalar, a plus and a minus actually means something physical. Right? And in terms of work, it's a question of whether the object is being sped up with the force, or being slowed down with the force, or is not responding to that force. Right? So when the work done by a force on an object is positive, it means that object is sped up. Okay? When the work done by a force on an object is negative, it means that that force is trying to slow that object down. That making sense? So if a force is doing positive work on a system, it's trying to increase the speed of the object. If a work is doing negative work on a system, it's trying to decrease the speed of the object. And if a work is doing no work, if a force is doing no work on a system, it's doing nothing to the speed of the object. Does that make sense? Right? And going back to those examples, it should make sense. F1 was the force responsible for pushing that object to a distance d. So you move that object to a certain distance d. So it's trying to move its speed along the direction of this thing. Friction is fighting it, it's trying to slow it down, doing negative work on this system. Right? And the normal force is doing nothing. It's perpendicular to this thing. It has no bearing on whether or not this object is going that direction. Okay? So always remember what that sign on work means. Remember, it's joules, it's scalar, and the plus and minus indicates whether you're trying to speed up the system or decrease the speed of the system. So that's F. Right, let's do one quick example before I let you go. So I'm considering a box pulled by a rope at an angle to the right. Right? So in this case, some component of this force along the rope, the tension in the rope, acts along the x-axis. I'll call that Fx. Some component acts, and it's only Fx, right? If you resolve Fx will be parallel to displacement, and Fy will be perpendicular to displacement. Right? So Fy doesn't work. Correct? Only Fx does something. And the amount of work done is Fx cosine theta, which is F cosine theta times d. So generalizing work in the direction of motion, theta is equal to 0, work is positive. Against the direction of motion, theta is 180, work is negative. Okay? If there are several forces acting, right, then the net work is the work done by the net force. Right? So there's two ways to get the net work. I can either find the individual work done by all the forces acting on the system and add them up, keeping track of the pluses and minuses. Right? Or I can find the net force. Right? And find F equals that of the net. Everyone following? Okay, I'm actually going to stop there. I will see you guys bright and early on Wednesday. Don't panic, just study and trust yourselves. Have you shot me any emails?
What?
Have you shot me any emails?
I shot you an email for last Wednesday, but last week you needed a time to take out, and I forgot to shoot you an email last week.
Shoot me an email with whichever one. Remember, it's
I just thought that was kind of funny.
It will tell you in the middle of the river. But that's your computer's Wi-Fi thingy.
Yeah.
Check your Blackboard participation scores. Those are always the ones that need updating. It's not really the clicker ones.
Alright, I'll go check the Blackboard.
Yeah, I missed the question.
Email.
It's like the same question, but it's the same thing.
Email me if your attendance has an issue. Email me. Right? Yeah.
For question 4 of the poll, it says I gave no
Don't
response.
worry about it. Just shoot me an email when your attendance.
Okay, yeah, it just shows that no one answered. So I just